Hello everyone, today we'll be looking at the molecule xenon difluoride and we will be solving for its hybridization. Firstly, what is hybridization? Hybridization explains the molecules that do not fit into the valence bond theory. It hypothesizes that the central atoms create new orbitals called hybrid orbitals before bonding with the surrounding atoms. So here are the steps that we will take to solve its hybridization. First, we'll be drawing the Lewis diagram of the molecule. Then we'll be doing the condensed electron configuration for the central atom. Then we will be turning that into a condensed energy level diagram. And then finally, we'll be doing the actual hybridization for this molecule. Alright, so let's start off with our Lewis dot diagram for xenon difluoride. So first, we know that this molecule is a non-octet molecule since the central atom is a noble gas, which means it can hold more than 8 electrons. So that means that we will not be using the Needham method for this molecule. So that means single bonds will be placed for all of the surrounding atoms. And then we will find our half number to fill in the valence electrons on the surrounding atoms and lone pairs, also known as non-bonding electrons, on the central atom if there are any. So let's start off by writing our central atom like this and placing our surrounding atoms around, on either side of the central atom. Now, the second step tells us to put single bonds for all the surrounding atoms. Now let's find our half number. So our half number basically tells us the total amount of electrons we have. So since we know that each fluorine has 7 valence electrons, and there are 2 fluorines, that will be 7 times 2, which equals 14. Xenon has 8 valence electrons, so that will be plus 8, which equals 22 electrons. We already used 4 electrons by placing our single bond, so 2 here and 2 here. So that we subtract 4, which equals 18. Now, let's fill in the valence electrons for the surrounding atoms. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So both of our surrounding atoms are full, and since we used 12 electrons from the 18 electrons, we will subtract 12, which gives us a remainder of 6. So this leftover will be placed on the central atom as lone pairs. So 1, 2, that is 1 lone pair. 3, 4, second lone pair. 5, 6, third lone pair. And that is our Lewis dot diagram for xenon difluoride. Okay, so now that we have finished the Lewis dot diagram, let's move on to the condensed electron configuration for the central atom. So for this, we need a periodic table. So the first step is to find the noble gas that comes before the central atom. So if xenon is our central atom, which is right here, then the noble gas that comes before it is krypton. And the second step, write the electron configuration from there. So, xenon. Let's start off by writing the noble gas that comes before it, which is krypton. Now, let's take a look at our periodic table and continue our electron configuration. So after krypton, now we're in our s orbital. So this is 5s2. We're passing these two. So that is 5s2. Now we are passing our d orbitals. So this is 4d10. And finally, to get to xenon, we are passing the p orbitals. So this is 5p6. And that is our condensed electron configuration for the center atom xenon. Alright, so now that we have finished our condensed electron configuration, we can move on to our energy level diagram. So the first step is to draw the diagram, separate it into different columns, and label the diagram, which I have done already. So the x-axis represents the types of orbitals. So we have the s orbital, the p orbital, and the d orbitals. And the y-axis represents energy. So the second step is to transfer the electron configuration info onto the diagram. So if we look here, the first thing we have is our noble gas, which is krypton. Krypton will be placed in the S column at the bottom, so over here. So let's go ahead and place that there. There, so we have krypton there. Now we have our s orbital, so that will be placed in the s column above krypton, and since the s orbital is single, it has only one dash. Like that, and it will be labeled 5s, like so. Moving on, we have our d orbital, so that will be placed in the d column, and since the d orbitals are a group of 5, there will be 5 dashes. So it'll be 1, 2, 3, 4, 5. It's labeled 4d, and this is higher than the s orbital since it has more energy. Okay, now, lastly, we have the p orbitals. So that will be placed in the p column, and since it is a group of 3, there will be 3 dashes. So 1, 2, 3, and it's labeled 5p, like so. Alright, so now we'll be placing our electrons. So if we look here, the s orbital has 2 electrons. So let's place our 2 electrons here. So one facing up like that, and the second one facing down like that. Now for our d orbitals, we have 10 electrons, and for this we'll be following Hund's rule, which states that each orbital gets a single electron before being paired up. So let's go ahead and give each orbital a single electron. So 1, 2, 3, 4, 5. Since we need 10, it can be paired up now. So 6, 7, 8, 9, and 10. So that is complete. Let's move on to our p orbitals. Our p orbitals need 6 electrons, so Hund's rule applies here too, since there are multiple orbitals. So 1, 2, 3, and now we do the pairing. 4, 5, 6. Alright, and that is complete. So there is our condensed energy level diagram. Alright, now let's move on to the actual hybridization of xenon difluoride. So here are the steps. The first step is to circle the outer electrons on the energy level diagram. So if we go back to our condensed energy level diagram, I have done that for us already. I have circled the outer electrons on our diagram, which are in energy level 5. Second step is to circle what is surrounding the central atom and make a list of what is needed. So for this, we need to take a look at our Lewis dot diagram. So as you can see, I have already circled what is surrounding our central atom. So first, we have a single bond, also referred to as a sigma bond. We have another sigma bond over here, and we have 3 lone pairs. So in total, we have 5 items around the central atom. So let's go here and make a list of what is needed. So as mentioned, we have 2 sigma bonds, so let's write that. As well, we have 3 lone pairs, so let's write that. Alright, so third step, draw an energy level diagram approximately the same height and length of the first energy level diagram. So I have done that for us already. Number 4, transfer the relevant information to the new diagram. So So as mentioned before, in our list we have 5 atoms, and on our Lewis dot we have 5 atoms around our central atom. So therefore, on our diagram we will have 5 dashes. So let's go ahead and draw that. 1, 2, 3, 4, 5. Now the first thing that we're going to take a look at is our sigma bonds. So let's remember that when doing hybridization, we are only looking at our central atom. So that means for each sigma bond relevant to the central atom, there is 1 electron. So that means if the first dash is representing our first sigma bond, we will draw 1 electron here. Our second dash is representing our second sigma bond. So same thing, we will draw 1 electron over here. Now let's go to our lone pairs. As you can see, each lone pair consists of 2 electrons. So that means if this dash is our first lone pair, we will draw 2 electrons here. This dash is our second lone pair, so we will draw 2 electrons here. And this third dash is our third lone pair, so we will draw 2 electrons over here. Alright, so the final step is to name the hybrid orbital. So to do that, let's first write the energy level which the hybridization occurred in. So that is energy level 5. Now to continue, let's take a look at our s, p, and d orbitals. So as we know, our s orbitals are single, so there's only 1 dash. Our p orbitals are a group of 3, so there will be 3 dashes. And our d orbitals are a group of 5, so we will draw 5 dashes. Alright, so since we have 5 items over here, we will cross off 5 dashes over here. So 1, 2, 3, 4, 5. Alright, so let's continue. In our s orbital, we cross off 1 dash, so that is just s. In our p orbital, we crossed off 3 dashes, so that is p3. And in our d orbital, we crossed off 1 dash, so that is just d. And that is the hybridization of xenon difluoride.
My name is Nithuya, and today we will be talking about the identification of any special bonds. There are many special bonds that are prevalent in the study of molecular chemistry. In this video, I will be talking about the first one, which is coordinate covalent bonds, and the second one, which is resonance structures. So the first one I will be talking about is the coordinate covalent bond. The coordinate covalent bond is a shared pair of electrons from 2 atoms. It is where the electrons come from one atom and not the other, and the other atom does not contribute to the shared atoms. So let's see here. Let's put this to the side, and as an example over here, I have drawn for an example, this would be ammonia, and this would be boron trifluoride. As you can see, there's a lone pair over here. And since I'm trying to put these two together, you want to bond this with it. This is like, it's bonding, it's sharing. As you can see, only one atom is contributing, not boron. Boron is not contributing, it's nitrogen. Nitrogen is contributing, and it contributes to make and form this. This is the bond that it forms, and this is what you call a coordinate covalent bond. See, it's a CCV. So the second special bond I'll be talking about is called resonance structures. The resonance structures are when the central atoms are placed with identical atoms surrounding them, while the location of the double bond changes. This can result in the strength of each bond being 1 1/3. Therefore, the electrons are being delocalized. For example, as you can see over here, this is sulfur trioxide. And as you can see, there's a double bond that's always being, like, the location is always varying. as you can see throughout these forms. And it's not going to be changing the number. It doesn't even change this molecule. It'll always be the same, but just the location will change, and it wouldn't really matter as much because, as you can see, the name still stays the same. So this would be a resonance structure. So according to the previously drawn Lewis dot diagram for xenon difluoride, which I have presented right over here, you can see that this covalent bond has 2 sigma bonds, as you can tell over here, has 2 sigma bonds and 3 lone pairs. Therefore, as you can see from this diagram, there are no coordinate covalent bonds and no resonance structures as well. Here I'll be describing the physical properties of the molecule. Before we go into that, we must understand the difference between intramolecular forces and intermolecular forces. Intramolecular forces are defined as forces that hold the atoms together within a molecule. The 3 types of intramolecular forces include covalent, ionic, and metallic bonding. As you can see here, the intramolecular force within the xenon difluoride molecule shows the connection of 2 fluorines atoms and 1 xenon atom together. This single bond connection shows that it's a non-polar covalent bonding. And this is shown because since xenon and difluoride are nonmetals that share electrons. In addition, since it's nonpolar, there is an equal sharing of electrons with identical electronegativities. Here is the intermolecular force. The intermolecular force is defined as a force that holds the molecules together. The 3 types of the intermolecular forces includes the London dispersion force, the dipole-dipole interaction, and the hydrogen bonding. The connection between one xenon difluoride and the other xenon difluoride is an example of the intermolecular force. As you can see over here, it's one molecule and another molecule. It's the connection between these 2 molecules. The intermolecular force of the xenon difluoride is called the London dispersion force. This force is the weakest of the intermolecular forces. It is a temporary attractive force from the temporary dipoles, which are unevenly distributed electrons towards the formation of nonpolar molecules. So as we all know earlier, the intermolecular force of xenon difluoride is the London dispersion force. And so the physical properties of xenon difluoride include that they are colorless and they have a crystalline structure. The boiling point is 155 degrees Celsius, and the melting point, as you can see over here, is 128.6 degrees Celsius. And this concludes my presentation about xenon difluoride. Thank you.